Okay, let's do some work here. Applications of the normal distribution. So starting off with this normal distribution, we are going to standardize it. All right, so this next concept that we're going to be talking about is a biggie. Biggerson, okay? So suppose that the random variable x is normally distributed with a mean, we know that symbol now, and a standard deviation, we know that symbol. Then the random variable is z is equal to x minus the mean over the standard deviation. Now here's what this actually means. Z-score, it's a z-score, is equal to my data minus the mean over the standard deviation. And I'm writing it like this because as we go forward, z-scores are going to be a big deal. You still have to know a z-score and what it is because that's what we're getting out of this deal. However, your data value is what's represented by this x right here. My mean, we've already learned several different representations for mean, right? This particular one is population, but what if I did x bar? Is that going to work? Yup, because it's the mean, or any type of mean that I'm looking for, whatever symbol is used, still the mean goes there. Standard deviation, we know that S is a sample standard deviation. Could that go here? Yes, because it's just a standard deviation. These are the typical symbols that are used simply because we're talking about population. We're just introducing this. We're making it all play real nice. But I want you to realize that this concept right here is an actual z-score. All right. This is normally distributed with a mean of 0, so starting down the middle, and a standard deviation of 1. So positive 1 to the right, negative 1 to the left. The random z, variable z, is said to have the standard normal distribution. So when I'm talking about z-scores, it is based on the standard normal distribution, that bell curve. All right? If the mean does not equal 0 and the standard deviation, standard, let me write that. I forgot part of that word, right? Deviation does not equal 1, then this formula, oh my handwriting today is leaving a little to be desired, isn't it? Formula transforms x into the standard normal variable z, where the mean is equal to 0 and the standard deviation is equal to 1. So whenever I have this, all right, we're basically what we're saying is we're getting something that's standardized or normalized. That's what it's a standard normal distribution. So if I have a mean and a standard deviation that are not 0 and 1, then I plug those into this formula and that makes it to where it's standardized. That's all that's saying. All right. So if my mean and my standard deviation are not 1, we're going to normalize it by making it a z-score. Now here's the deal whenever it comes to a z-score. This z-scores are the number of standard deviations from the mean. That's what a z-score actually is. So my normalization is saying, oh, here my mean is 0 and it's 1 stand for the standard deviation. La, la, la. So when I'm talking about a z-score, my mean is just in the middle. All right. And however many standard deviations away, that's what my z represents. That's the z part. All right. This equals, whenever I'm looking at this, how many standard deviations away, this is going to represent the area to the left of the curve. Now remember, when we were talking about our normal distribution here, right? So we had these normal distributions. Remember, we used a couple different words and we said they were the same. And then we interpreted those words. That's the same thing as a proportion. That's the same thing as a probability. That's an R in there. And this is area under curve. All of these mean exactly the same thing. Those are all synonymous, and they all represent that value. Crazy, right? So it's that area under the curve, how many z-scores away, which is also going to tell us probability, which is also going to tell us proportion. Do you see why this is awesome? This is awesome. Okay, just letting that sink in for a second. All right, let's try one. And as we do this, I want you to see what the z-score is, and we're going to look at the z-score, but I also want you to, we're going to use StatCrunch in order to do our actual computation associated with this, but the concept of a z-score is still a biggie, right? You still have to understand the concept of what the z-score is. Okay, so a pediatrician obtains the heights of her 3-year-old female patients. I'm going to scoot this up so you can see this chart and everything. Let's see here. The heights are approximately normally distributed, so that's good to know. Here we have a mean of 38.72 and a standard deviation of 3.17. Is it 0 and 1 right now? No. So what do you think we're going to use in order to normalize it? Right? Okay. Use the normal model to determine the proportion. What did we say proportion was again? Man, I should just peek the whole thing. Oh, the proportion is also associated with this area under the z-score of the 3-year-old females that have a height less than 35 inches. So my height here is going to be, let me get a new color, less than 35 inches. Okay, so I want this proportion. I want to figure out what that means. Now, I want you to really understand where this is coming from and what these values represent. So we are going to, I'm going to draw this out because I want you to really see how this plays. Our mean is 38.72. That means 1 standard deviation away. I'm going to write these sideways here because I think that we're going to be able to see that easier then. So I'm turning my iPad even though you can't see that, but you get the point here. So I'm going to change this up to be 38.72 so that we can get all these numbers in because the numbers are so big. 38.72. And then going in this direction, I'm going to add 1 standard deviation. So I'm going to add 1 standard deviation to get to, plug that in your calculator, I get 41.89. Is that what you get? I'm going to subtract 1 standard deviation from 38.72, and what do you get? 35.55. That's what I get also. Is that what you're getting? Okay, so I want to look at a height less than 35 inches. So that tells me that my value I'm looking for here is, this would be right here at 35, and I want less than 35. So this is the area, this is the proportion. So if I'm looking at this, I am more than 1 standard deviation away to the left. All right, so let's see how this all plays out. So z is equal to x minus the mean over the standard deviation. So z is equal to my data. Remember, we talked about that being the data, which is 35, minus my mean of 38.72 divided by my standard deviation of 3.17. Now, the one thing that I will say is make sure whenever you're looking at this, you put parentheses around this numerator, because if you plug all this into your calculator is going to do order of operations. It needs to know that this is all in the numerator. Okay, and what do you get? I get a -1, 2 decimal places. negative 1.17. Here's something that we hadn't talked about specifically. It's on this chart up here, but look at this. This says negative 1 and this says positive 1. Here's the whole moral of this story. Positive z-score just means to the right of the mean. A negative z-score just means to the left of the mean. It doesn't have a physical numeric value. All this means is to the right or to the left. If it's positive, it goes to the right of the mean. That means it's above halfway, right? Because that's what we determined. Our mean is in the center, and so it's above halfway. If it's a negative z-score, then it's to the left. It's below halfway. Now look at what I just want you to make these connections. This is negative 1.17. Here is my mean. Here is one standard deviation, and we know it's just a little past based on our numbers. Does it make sense that this is to the left 1.17 oh my goodness, got tongue-tied there. To the left 1.17 standard deviations. That's what that actually means. This means to the left 1.17 standard deviations. I don't want to write that big word all the way out. That's what that means. All right. And I know that this says less than. So whenever we're going to do the actual calculations of what the proportion is in StatCrunch, all right, but this is going to help us understand what's going on here. Okay, so I'm going to scoot over my notes. So hang on to yours and we're going to look in StatCrunch. Now, this is called normal distribution, right? This is normally distributed. I'm going to scoot this over here just a little bit so you can see that right there. Normally distributed. So when I go to my calculators, I'm going to hit normal because it's normally distributed. Now look at this. If my mean is 0 and my standard deviation is 1, do you see this? I know it's kind of small on your screen. Let me make it a little bit bigger there. That's helpful. So that's what makes this normally distributed. But if my mean is 0, my standard deviation is 1. This is the chart that we have. Now, we said we can use our z-score in order to figure that out. And we know the area is always to the left because this is less than. So then we come over here and we say, all right, that's cool, but let's get our information from our chart. We plug in the mean. Ooh, let me scoot over a little bit more. We plug in the mean, the standard deviation, and it's less than 35. So this is my data value. That's what we plug in, that less than part with the mean and the standard deviation. All right. Okay. So I'm going to plug in my mean here is 38.72. My standard deviation is 3.17. And this is less than, and we know that we're going less than 35. Oops, I got an extra 0 in there. Less than 35, then you click compute. All right. And when I click compute, this is my value. Let's take it to 4 decimal places. So what does this give us? 0.1202, 1202, 03, sorry, because that's a roundup. 1203. All right. So we have, oh, you can't see this. I'm writing on my thing and you won't be able to see it. Oops, too far. 1203. So, therefore, oops, I'm going to change my color. I'm going to go back to blue. Therefore, the proportion of patients that are less, that looks like O-R-E, not A-R-E. Wow, my handwriting, you guys. That A-R-E, less than 35 inches is 0.12. I already forgot. Do you remember? 1203. I'm glad you guys are on it. That is the proportion. Remember, probabilities between what? 0 and 1 inclusive. Proportion is representative of the same thing. We are looking at decimal values. These are not percentages. Now, if I wanted to think in terms of a percentage, I just move it 2 places, right? So about 12%. And does it, right? Look at how small this is that we're going with. That makes a difference. Now, I'm going to scoot this up. The next part of this, just because we're making all these connections on this first part, it says, look at table 2 for the actual data, which is right here, and see how it compares. We want less than 35. So I'm going to make this a little bit bigger. So if I have 35, right is right there, and I want less than 35, we're going to add these up. So my actual data is 0.005 plus 0.005 plus 0.005 plus 0.025 plus 0.02 plus, what's the last one? 0.055. Okay, plug in all those into your handy dandy calculator, and what do you get? I get 0.115. This is the actual data, 0.115. Let me get a highlighter here. This is my actual data. This is predicted. Oh, dang it. Why did it change my colors? Oh, well, that didn't help, did it? Predicted. This is predicted based on the information that I have, just like any bell curve, right? We've talked about this. And look how close it is to my actual data, right? We are looking at 0.12, 0.1, and if I round this up, 0.12. You see what's going down there? That's dang close. And that's what we're talking about. All right. So in lieu of going through all these infinitely many pieces of data, it seems like sometimes we can use this z-score in order to figure out, okay, what is that proportion? What is that probability? What is that area under the curve? Because all of those are the same, right? So these are so close. So close. And that's the deal. And that's why we use these z-scores. It's pretty cool, right?